In this video, we want to take a look at monitoring pre-membrane and post-membrane pressures and venous line pressures of a conventional ECMO circuit, and using those pressures as well as the flow data to determine whether or not you have a preload or an afterload problem. So let's look at our system here. We've got standard, we're using the center mag system here. We have the Quadrox oxygenator, and it's a conventional ECMO circuit all around this with a venous line that comes down to the inlet of the center mag pump. The outlet of that pump then goes into the pre-membrane side of the Quadrox, and the post-membrane side of the Quadrox continues up. We have a blue stripe on our venous line, and a red stripe on the arterial line, and the flow probe right there. The pre-membrane side of the oxygenator has a line connected to P1 on the back of the center mag, and that's displayed over here. We'll calibrate that in a second. The post-membrane side of the Quadrox is connected up to P2 on the back of the center mag, and that is being displayed here. I've already calibrated that and set my limits. The flow is being monitored here. The flow is being displayed over there on the screen with a flow of 4.93 liters a minute at an RPM of 4,200, and I've set some brackets of 4 liters and 6 liters around my flow of approximately 5. Let's go ahead and calibrate our P1 sensor here, just as a reminder of how we do that. So first we can come down to the transducer. This is P1, goes to the pre-membrane side. We're going to turn that off to the pressure source and remove the cap, and keep that cap sterile by setting it aside, not letting it touch anything. Now the stopcock is open to air. Atmospheric pressure is what that transducer is feeling. We can come into the menu system here, press the menu, and then continue to press that button to drop down to pressure menu. Now we're at pressure menu. We can just select enter. We enter that, and then drop down to pressure calibration and do new. Select new there, and cal P1 is the top option for the up arrow. We are open to air down here, so this is the time to cal P1. Now we're calling, it's flashing, and it reads a number. Let's close this menu. We can touch the RPMs and then exit the RPMs, and that closes all those menus. Now we're reading 0 on P1 because we're still open to air, and we're reading 237 on P2. That's what it was reading previously. And we're getting a calculated number of P1 minus P2, otherwise known as the delta P. That delta P is minus 237. This is a subtraction of the two there. So let's turn the stopcock here. We'll open up P1 and put our sterile cap back on this to keep it clean. And we're reading 256 on the pre-membrane side and 237 on the post-membrane side with a delta P of 19. 19 is not too far off of what we suggest that it would be clinically, of 5 millimeters of mercury per 1 liter of blood flow. That would say that we should be at about 25. We're at 20. This is room temperature tap water as opposed to 37-degree blood, so it all kind of makes sense, and we're happy with that. Now, in addition to monitoring pre-membrane pressure and post-membrane pressure on P1 and P2 of our center mag system, we also have the venous line pressure tapped in. I put this in here just for this demonstration. Clinically, we wouldn't normally cut the venous line like we've done here. Here I cut the venous line and put in a 3/8 straight lure with a lure lock, and I connected that up to our red box disposable set. There's a risk associated with this. We'll try and demonstrate it at the end of the video. If I open this stopcock, it'll suck in air because, as you can see, we're reading minus 53 right now. Let's confirm that the 0 is accurate here. I'm going to turn this off to my circuit and take this stopcock here. That's part of the DLP set. And I'm going to turn it so that it's off to the circuit but open to my pressure transducer, like that. And we'll check this up here. It's in the mean mode, so it's going to take a moment for it to adjust. I'm going to set that down at the level that it's going to be resting, and we see we're reading 3. So let's put on instantaneous, and then let's adjust the 0 till it reads 0. We can put it back to mean. Try and not bump that knob because it's always active. And then we'll come back down here and turn this stopcock so that it's off to air and open continuous with the circuit, like that. And you saw that bubble jump there. That's one of the reasons we don't mess around with this venous line. That negative pressure just sucked that bubble down in, and I heard it go over there and hit the pump. So if we're really going to do that clinically, we'd probably have to be real super careful to put a red cap on that before we did anything moving around, and not open and close this if there's any bubbles in this line. But we're doing a demonstration of preload and afterload resistances. So what's preload? Preload is everything before this pump. So here's our pump, and this whole venous line up to the patient, the size of the cannula, the position of the cannula, the volume status of the patient, the position of the cannula inside the patient, the position of the patient on the bed. All these things factor into the preload. And this pump is preload dependent and afterload dependent. So if it, just like the heart, if it has difficulty filling, that's the preload. If it has difficulty filling, then it has difficulty pumping. And it's also afterload dependent. So what would be the afterload of this pump? That's everything after the pump. So it's this piece of tubing before it gets to the oxygenator. It's the oxygenator. It's the arterial line all the way up to the patient. It's the arterial cannula. It's the SVR of the patient. It's the position of that cannula inside the patient as well. All those things contribute to the afterload of this pump. And just as it is with your native ventricle, if the pump has difficulty emptying, if it has a high afterload, then it pumps less well. So let's demonstrate then what happens when we cause preload problems or afterload problems, and we're going to simulate that by placing a tubing clamp on either the inlet to the pump or the outlet, the arterial line of the circuit, the outlet of the entire circuit. So here let's note our pressures. We're at -50 on the venous line, 250 and 230 on your pre and post membrane pressure at 4,200 RPMs and just about 5 liters of flow. Here comes some venous resistance. Give that a moment to update, and we can see that now we're more negative in the venous line. We have lower flows, and we have lower oxygenator pressures, and that makes sense. These pressure systems over here that are monitoring the oxygenator, they can't see this clamp. They only look forward. They can see the oxygenator, or the P1 can see the oxygenator. P1 can see the oxygenator, the arterial line, the cannula, and the patient. P2 can see the arterial line, the cannula, and the patient. And they don't know what's behind them. And this clamp is ultimately behind them on the venous line. So all they see is the flow is lower, and pressure equals flow times resistance. If the flow came down, then the pressure comes down, because the resistance, as far as they're concerned, didn't change. But this one on the venous line pressure is more negative. At the same RPMs, we generate a more negative pressure and get lower flow. So this is a clear indication, if you have a venous line pressure, it's a clear indication that you have a preload problem. When this becomes more negative and the flow comes down at the same RPMs. Let's relieve that and go back to our baseline status here. And we see that without any additional resistance, then we're at 5 liters, 250, 230 or 240-ish, and -50 over here. Now let's add some resistance to the arterial side. We see the flow came down, the pressures went up, and the venous line pressures less negative. It's closer to 0. It was -70, now it's -9. So it's a more positive number. And this makes sense. The venous line pressure can't see this resistance out here on the other side of the pump. It can't see the arterial line. It can't see the oxygenator. What it knows is that the flow has come down, so it doesn't have to suck as hard to get that much flow because the resistance hasn't changed. Pressure equals flow times resistance. Resistance is the same. Flow is lower. The pressure is going to be, you have less pressure required to do that. On the other hand, if you look at the pre-membrane and post-membrane pressures, they can see the oxygenator, the arterial line, the cannula, and the patient, and there's a clamp on that arterial line. So what they see is a higher resistance. That higher resistance causes the pressures to go up and the flow to come down on this afterload dependent pump. All right, before we leave this, why don't we set up some scenarios for you where I'll clamp things that you don't know what I'm clamping, and you read the data, and then you see if you can figure out whether it's preload or afterload. So here's how we're going to do this. I'm going to shield your view with this towel, and then we're going to apply some clamps, either to the venous line or to the arterial line. You read the screen. Right. Okay, here's your first test. Note your baseline, minus 40, positive 220, positive 200, about 5 liters flow. RPMs are 3,800. Are we providing a preload or an afterload problem? The flow came down. The flow always comes down. That's not that helpful. The flow came down. The oxygenator's pressures went up. And the venous line pressure is less negative. It's closer to 0. It also went up. So the answer is afterload. Very good. All right. Going back in. Ready? Flow came down. Flow always comes down. Nobody's ever called me to complain that the flow is too high. They're always complaining the flow fell. So our flow is lower. We have a preload or an afterload problem. Venous line pressure is more negative at the same RPMs. Oxygenator pressures are lower and the flow is lower. The resistance is not over there. The resistance is over here. Good. You guys are awesome. All right. Let's do something else. Let's get rid of this. What if you didn't have the venous line pressure to look at? You only have your oxygenator pressures and your flow. And that's what you would typically have on a non-cardio help system, because we don't put the openings into the venous line. All right. What did I clamp? The flow is lower. It's always lower. Oxygenator pressures are lower. Those two make sense. The problem is not afterload. Must be preload. And it is. Okay. Flow is lower. Line and the oxygenator's pressures are higher. Lower flow, more pressure, must be greater resistance. It's a post-oxygenator afterload problem. All right, great job. Okay, let's talk about another way that we can use these pressures. We have here our ECMO initiation checklist, and it goes through a number of items that we can talk about at another time. When we get down to the end here, it's talking about how you would be increasing your flow as you initiate. And it says increase flow towards target at over 1 to 2 minutes. And then stop if, and it gives you 3 conditions under which you're going to stop. Stop if your RPMs are greater than your blood flow and your arterial line pressure is less than 300. If you find yourself in that situation, then you have a preload problem. What's that mean? So let's look. Our RPMs are 4,100 RPMs. Our flow, if you were to express that in milliliters instead of liters, would be 4,050 or 4,040. So the RPMs are lower than the blood flow. And that is a really, it's not that sensitive, but it's a really good indicator. If you ever find yourself in a situation where your RPMs are greater than your flow in milliliters, then you have a resistance problem. And what you're unsure of yet is whether or not it's a preload or an afterload problem. And that's where the thing goes, and the checklist goes through and describes that the RPMs are greater than the blood flow, and your arterial line pressure is less than 300, then you have a preload problem. But if your RPMs are greater than your blood flow, and your arterial line pressure is greater than 300, then you have an afterload problem. So you would be looking at the arterial cannula. So the scenario here is, just say for instance the surgeon just put the cannulas in, and you're initiating flow. You go through all the necessary steps, and that first step, of course, would be to add some RPMs and take the clamp off. So let's stop this pump. Okay, we're going to stop the pump. We're going to put a clamp on the arterial line, as would be good practice. Have a clamp on the arterial line while you're initiating. Surgeon says the cannula is in, or you're ready to go on ECMO, and you go through your checklist, and you confirm that your checklist is complete, that you've verified that all this works. If heparin has been administered, and you've reached a target ACT, that the cannulas are in and de-aired, and that the circuit pressure is greater than the patient pressure at the cannulation site. What is that? That says increase the RPMs above as necessary to achieve this condition. This condition is a replacement for what the instructions for the pump say, which is you have to have a certain RPMs before you take this clamp off. And the manufacturers give you a number like 1,000 or 2,000, and it's a generally safe number. But we could be more sensitive to that. And here the situation would be you've got these line pressures, and today we're just hooked up to a bag over here, so we're just getting a static number. But if this pressure was being generated by the patient, then let's see, where are we? We wouldn't read it because our pressure monitors are down here. So let's move this clamp back here to the outlet of our pump. Now with the clamp at the outlet of our pump, we can stand over there on our side of the pump, and we can reach this clamp if we want, just reaching over our pump. And in the meantime, the pressure that's coming off of our patient will come down here, and it will push on these transducers, and we'll get a number that is reflective of the patient. And so this number of 72 and 71, let's say, for instance, we're initiating VA ECMO, and that is the patient's, that's what we're reading. That should be similar to the patient's arterial blood pressure. So if that's the arterial blood pressure, then what you would do is, with a clamp over on this side, you would increase your RPMs until you had a number greater than 72. And in this situation, I can't show you that it can be less than that because my bag is up in the air. But you would push this number, push that tag there, and you would start adding RPMs to this. Now we're starting from 75, so you would have to increase the RPMs enough. So let's, for instance, say we need to get to 140. Now, if 70 were 0 in our case, then we need 1,800 RPMs to produce another 70 RPMs. So in your, this isn't a perfect example because this is connected to a static bag, and I'm reading it from both directions. So the take-home message for you is that when you initiate ECMO and you get to this stage where they say go on ECMO, before you take your clamp off, you have to have a certain number of RPMs. The manufacturer will give you a default number of, say, 1,000 or 2,000, but you can be more sensitive than that. you can make sure that you clamp here and read the pressure in your circuit behind this clamp. Patient's over there, your pump is down here, your transducers are down here. And if you increase your RPMs until your line pressure is greater than what you're reading up there on the patient's hemodynamic monitor, then you'd be safe to take this clamp off. And if that happens at 1,000, great. If it happens at 1,400, then that's what you need is 1,400. And of course, you should understand that that would be a much lower pressure and lower RPMs if you're initiating VV ECMO, because this arterial cannula would be connected all the way over to a vein if you're doing VV ECMO. So it's going to be the height of the table, which is the column of fluid, the height of the table, and the patient's CVP that you're trying to overcome. But if you're doing VA ECMO and the cannula is in the aorta or arterial branch, then it's going to be the height of the table and the patient's arterial blood pressure. So you'd need greater RPMs to initiate VA than you do for VV. So here we are on that checklist, and it says increase the RPMs to achieve a situation where your circuit pressure is greater than the patient's pressure. And that's what that means. Place your clamp, make sure you're measuring your pressure, compare that to what you see on the patient's hemodynamic monitor, either their CVP or their arterial blood pressure. Set your sweep gas rate to 1:1 with your targeted blood flow. Remove the clamps, and then, while watching the cannulas, confirm forward flow. Now, if we're just initiating flow for the very first time, I probably wouldn't have a bracket way up here at 4 liters a minute, because I know for the next couple minutes I'm just going to be reaching that. So let's get in there and turn that off, or it's really going to annoy us. And we'll step down to the minimum flow alert, and we'll decrease that. We'll decrease that minimum flow alert right now to essentially 0 until we get on and stabilize this patient. So your minimum flow alert is now 0. So now I can slowly step up our flow, enter the RPMs, increase our flow, and I'm going to increase until I reach one of these 3 conditions. My RPMs are greater than blood flow and the line pressure is less than 300, or my RPMs are greater than blood flow and the arterial line pressure is greater than 300. Both of those tell you you've got a resistance problem, or you reach your targeted blood flow. Now, we've been teaching that the ELSO says 60 to 80 mils per kilogram, but in our experience, 50 is a pretty reasonable number. So if you're at 50 mils per kilogram, this is an 80 kilogram patient that we're shooting for 4 liters. Let's keep increasing this. And as we increase over 1 to 2 minutes, let's see that this number isn't greater than that number. But there we are. Now we're increasing our RPMs. The 3,400 is less than 3,800. And we keep increasing until we reach our flow. Well, we just reach our target flow of 50 mils per kilogram of 4 liters a minute. Our line pressures are less than 300, and our RPMs are less than our blood flow. That's good. We're happy with that. What we were seeing earlier before I did our simulation magic, that's the sensitive thing you can do with these pressures on initiation. You could, if you had, let's go back to our 0 again. And turn everything down, and we'll start from the beginning. We'll misplace this venous cannula by making that clamp up there a little bit tight. And we'll put a clamp over here on the arterial side, and the surgeon says, "Are you ready to go on ECMO?" And you'd say, "No, my RPMs are 0. I need to make my RPMs such that these line pressures are greater than the patient's arterial or CVP. So let's get on that." And now I've got a circuit pressure of 120. That's probably going to be greater than either the CVP or the arterial line pressure. So I'm going to say, yes, I am ready to go on. I'm about 1,700 RPMs. I take the clamp off. Okay, we're going on ECMO. Turn on our sweep gas over here. We're going to turn on the sweep gas to equal to our anticipated blood flow rate, which was 4 liters a minute for this patient, 50 mils per kilogram times 80 kilograms. And we're going to start increasing our flow until we hit one of those 3 stop points. Either we hit our top flow, or we hit a line pressure of 300. And if it is 300, then we're going to look back and try and figure out whether it's preload or afterload. So we're increasing. Wow. So our Our RPMs are 3,000. Our liters per minute are 2,300, 2,400. Let's say we're not really confident about this. So let's keep going. And, well, my line pressure is a lot higher. It's 800 RPMs more than our blood flow in mils. Or like 4,500. We're only at 3,400 over here. This is a bad situation. We should be very cautious, and we should be calling this out to the surgeon. Our line pressures are low. They're nowhere near 300. Our flow is low. Our line pressures are low. This is not an afterload problem. It's a preload problem. So we got to call that out. Doctor, are you happy with the position of that venous cannula? Also, of course, before you do that, you look around for any kinks on your side. You've got bad data. It's either your fault or it's their fault. Make sure it's not your fault before you start asking them to fix their things. So let's redo this now with an afterload problem. So I'm going to back that clamp off for you so that it's not a problem. And I'm going to tighten this venous clamp. And we're going to turn this pump off. And I keep increasing my flow, and we find that our line pressure, 3,500, flow, 2,200. That shouldn't be higher than that, ever. And our line pressures are over 300. This is a stop point. We hit our highest acceptable line pressure. Our RPMs are greater than our LPMs. This is a problem. We have a high resistance, and we know the resistance is on the afterload. Doctor, are you happy with the position of that arterial cannula? Of course, you've checked your arterial line to make sure it's not kinks of your side. You can kink out of the oxygenator or something simple like that you should be fixing because it's your stuff. Okay, hope that helps you with the how to use these line pressures and the other data, flow and RPMs, while you're initiating ECMO. Okay, so if we've talked about the venous line pressure and how it monitors the venous line from the cannula to the venous line all the way down to the inlet of the pump, we've talked about the arterial line pressures, or the pre-membrane and post-membrane, or P1 and P2, or P-int and P-art if you're looking at the cardio help. We've talked about these pressures, and one of them starts here and includes the oxygenator, the arterial line, the cannula, and the patient. And the other one starts here and includes the arterial line, the cannula, and the patient. Then you might see that we've got a gap in our investigation here. We can see the entire venous line if you have a VLP. And you can see the oxygenator through your pre-membrane pressure. And you can see the arterial line, cannula, and patient through both your pre-membrane and post-membrane pressure. So there's this section right here that isn't monitored at all. So what happens if we kink this line? And how could you possibly kink that line? Here's how you could kink that line. Look, there's the outlet of the pump is here, and the inlet of the oxygenator is there. And if you go out on a transport and you're holding this cart next to a patient's bed, things start to bump up against each other, and these brackets shift, and maybe this line gets kinked like that. So what does it look like when you have high resistance in between the two sources that you can monitor? We're going to kink this right here and watch. The venous line pressure became more positive. The oxygenator's pressures became less positive, and the flow came down. So this says it's not in the arterial line. And this one says it's not on the venous line, so the place left over is that gap in between the venous and the arterial line. Now I relieve the kink. This becomes more negative. These become more positive, and the pressure goes up. If we put a kink down here, the other end of that tubing, right here at the inlet of the oxygenator, flow comes down, pressures come down. That makes sense. It tells you there's no problem after the oxygenator. And the venous line pressure, if you had that, it goes up while the flow comes down. Says there's not a problem in the venous line. That leaves this. Now, if you didn't have the venous line pressure, then a kink in this would look like a venous line pressure problem, a venous line resistance or preload problem. And so if you checked out the preload, then you better check this one too. Or this is really short and simple and easy to check. Check this before you start repositioning cannulas and stuff like that. Okay, so there's one last section that we have to talk about, and that's this area right here, the oxygenator itself. Now you'll notice if we take a clamp here and watch your P1 and P2, watch the pre-membrane and the post-membrane, as we add resistance to the arterial, then these numbers go up, and they go up together. They both went up. And if I remove the resistance, then they both come down. So under normal conditions, these travel up and down, and the only difference between them is the resistance in the oxygenator itself here. So if there's growing resistance in the oxygenator, then what you see is the pre-membrane goes up. It gets further and further away from the post-membrane. And it's difficult for me to simulate because I can't actually get in there and create a high resistance. So we have to use total smoke and mirrors on that one. And if you wanted to see how that would play out, then what I have to do is simply lie to this transducer and tell it that it's feeling a high pressure and let it believe it's coming from the oxygenator. So if I turn this stopcock off to my oxygenator and I start applying pressure here, you can watch P1 start to climb while P2 is holding steady. And this is what a failing oxygenator would look like. Difference is, it doesn't happen this fast. It probably happens over many, many hours, days maybe even, before you get this kind of a difference of 200 millimeters of mercury, when normally it's 25. So the rising delta P plays out as an increasing pre-membrane, but generally until the end moment, it's an unchanged post-membrane. The resistance has to be so bad in here that it changes your flow before it affects that number there. Okay, so we moved a few things around now, and you can see your venous line pressure right here, and you can see the stopcock that is attached to the venous line right here, and then there's about 5 feet of tubing that goes to the inlet of this pump. Currently, we're measuring a venous line pressure of minus 48, which is very reasonable pressure. We're very happy with that if we're on ECMO with a minus 48. Sometimes it can be as low as minus 100. We say the normal range is minus 50 to minus 100, and I've certainly seen it lower than that, minus 125. There's some places that don't measure it at all, so they're going to see. They would see if they were looking very, very low pressures. So let's see how long it takes. If I had the stopcock incorporated into my venous line, and I accidentally opened it, how long until this pump deprimes? And we hear alarms over there because our flow has dropped as a result of air embolus. So here we are, minus 40. And I'm going to turn this to open in, keep an eye on the pump here. The line is opening in 3, 2, 1, now. And I'm turning it off. That was pretty instantaneous. Maybe we go back and watch it in slow time, but it was less than 2 seconds. And that is why we generally don't include openings on the venous line for an ECMO circuit.